just let me know if you are able to click on the link or join the group. And in this case, we can start the session, I think. So if everything is clear, now we can start the session, and you can also join the group if you want. Yes, are you able to join the group? Just let me know whether it is working or not. Okay, so I can also add you. You can type in your number, mobile number. I can just add you to the group in that case. Okay, I will just add you. Because that group was formed just for the purpose of discussion, right? In case we have any postponements and anything, we can just update. So I think I have joined. I have made you join the group. Yeah, I think you are in the group now. Okay. So if you have any doubts, you can just post in the group. And meanwhile, we can start the session, right? So I think the screen is visible, right? The PPT and everything is visible, and my voice is clearly audible, right? So this week we are actually focusing on some measurement topics where you have the various kinds of instruments for voltage and current measurements, and also the watt meter and the energy meter. Because other than voltage and current, we need to measure power and using the watt meter, and also the energy that is in your home. Basically, you use by default the energy meters when the connection, the electric connection in your home, that is passing through a energy meter, which is used by the distribution company people to actually take a note of the readings or take a note of the consumption readings, so that they can charge you for that, how much amount energy you consumed, right? So that is a energy meter which is mostly there in everyone's home. The energy meter also will cover, and then we'll move to the digital, where the most important part is the oscilloscope, right? And how do you interpret various plots, XY plots from there? How do you get the information of an unknown signal from a known signal, reference signal, that we can also see, and that will construct the topic, right, of measurements. That is the whole point, and the areas you need to focus for the measurements part. So you are able to see the screen, and if there is no doubt or if you don't want any discussion other than this new measurements week content, so we can just proceed, right? Otherwise, if you have any doubt from the previous weeks, we can just have a discussion on those things also. Because we placed the extra session solely of the purpose for discussion regarding the machines, right? Electrical machines, transformers, including transformers, induction machine, synchronous machine, and also the mutually coupled coils. Some discussion on that was also, some problems also we have seen, extra problems. So I thought to place the extra session, and that's why we did an extra session out of the total 12 sessions. But this week we are focusing on measurements, right? So if you have any doubt, you can just let me know anywhere. And today we have the last session, so if you have any doubt, it is better to get it cleared. So any doubts, if you have, you can just let me know anytime by stopping me. Any doubts from the previous week is always encouraged. If you have any doubts, you should clear it before the exam, right? Because the exam is nearby, so you should not have any conceptual doubt, right? All else, you can just post in the group anytime you have any conceptual If you need any conceptual clarification, you can just go ahead and post in the group also. So I think it will not be a problem. So if there is no more doubt, I think I can proceed to the week's content. And basically we'll learn the concepts through the discussion because the concepts are easy, and we'll just deal with the basic instruments first, the PMMC type instrument and the moving iron type instrument for measurement of voltage or current, as you know. So those two are very popular instruments, and basically we use them in the laboratory for measurement of voltage and current, right? But the working principle of both of them are different, and both of these types of instruments actually show different parameters of the signals that you are measuring. Basically, we are in power engineering, we are actually dealing with voltage and currents, and the working principle is also based on the both the PMMC type and moving iron type. Basically, there is the interaction of magnetic fields also, right? So you need electric current for excitation. Maybe you force it with a voltage, it will convert it into a form of current and give the deflection, and you take the reading in terms of voltage, you linearize it if it is a linear instrument, because you know V by I or V by Z is nothing but current. So either you take some current readings by connecting the meter in series with the network. The current is responsible for the torque, right? Which is obvious. But if you want to measure the voltage across two nodes of a network, let's say you have an element and you want to measure the voltage, it is a different network, I think, and you want to measure the voltage, you connect it in parallel. And if you want to measure the current, you connect it in series. These are basic fundamentals that you need to know, that how to measure a current and how to measure a voltage. For measurement of current, always connect your instrument leads in series to the network branch through which you want to measure the current. For measurement of voltage, you need to connect the instrument in parallel to the nodes across which you want to measure the voltage. These are very fundamental principles. Now tell me one thing, if you want to measure the current or measure the voltage without any loading effect, because you know that if you want to measure some current, let's say 5 ampere, you need to place or connect the meter also, right? So that the meter also knows how much is the current. In lab also you do like this, you connect in series to the branch through which you want to measure the current. But what is there is that this meter also has some internal impedance or resistance, simply you can model. So this meter will also have some loading effect on the network. What do you mean by loading effect? That let's say this is 5 volts, this is 1 ohm. Without the meter, if you have connected the network, the 1 ampere would have how much? 5 by 1, 5 ampere would have flown. Understood, right? But this meter may have some resistance. So let's call it R meter. Then 5 by 1 plus Rm ohm is the current. And obviously Rm is greater than 0. So I is now less than 5 ampere. So this is what is known as loading effect. Clear? Yes or no? This concept is very important. So do you want this loading effect or do you not want this loading effect? Both for your ammeter or whatever you call it, or your voltmeter. Basically the current measuring instruments, they call it ammeter, and the instruments they use for voltage measurement in electrical engineering, we call them voltmeter because they measure voltage. But in both cases, do you want any loading effect or not? You don't want that you connect the meter or connect the instrument in any fashion for measurement of voltage or current and the value changes. It is not desirable, right? Because the measuring instrument should not have any loading effect on the network. So loading effect is not desirable. This is the first and only rule behind the design of the meters, that they should be designed in such a manner. First of all, the principle is that to measure current, you connect the instrument in series to the branch, and to measure the voltage, you connect the meter or the instrument, which you call the voltmeter, in parallel to the node across which you want to measure the potential difference. So with that keeping in mind, also the rule is that you don't want any loading effect. So can you tell me in both cases how to avoid loading effect? What should be RM for both cases? For M meter, RM should be kept as per design, high or low. For voltmeter, because this is a design constraint, right? RM is the meter resistance, which is as per design. Okay, so if your voltmeter RM is 0, that means negligible impedance. If it is so, then when you connect the meter, then it will short the resistance, and then it will not give us the true value of the voltage. It will have a severe loading effect. So your voltmeter impedance, if it is very low, the meter only will take a lot of current, right? A short circuit kind of current when you connect in parallel, because that element across which the voltage you are measuring, that may have some voltage, but when you connect a low impedance meter across it, it will show you almost zero reading because it is having a very small resistance, and that will consume a lot of power, which is not desirable. Power loss also will be there. So for parallel connection, your which is your voltmeter connection, the RM should be kept very high, almost infinity. Then in that case, what will happen, that when you connect the voltmeter in the shunt or in parallel to the element, that will almost be like an open circuit, and that is desirable because the current drawn by the high impedance shunt meter is very low, as well as the it will not have any significant loading effect, because what you know, parallel combination of two resistances is what is less than the lowest resistance. You should have known this, that parallel combination of maybe infinity ohm and 2 ohm is almost less than 2 ohm. So it is not having any loading effect. It is not changing the R value, right? Actual R value in the network effectively. So we say that the meter does not have any loading effect. Similarly, can you tell me that for M meter, no, you are getting confused. I am not talking about what is there inside the meter. Don't go into that. I will cover that. I am talking about the effective impedance of across the leads of the meter. Because in voltmeter, you connect the voltmeter in parallel to the node across which you want to measure the voltage. Now, what is there inside it? Forget about it. Okay? I am not talking about the internal resistance of the meter and how to convert a PMMC instrument into a voltmeter or an ammeter. I am not telling about that. I will go into that. But I am talking about the effective impedance that the meter or the voltmeter should have. So ideally, any type of voltmeter, may it be PMMC, may it be moving iron or any type, should not have a very low impedance. That is the thing we are discussing. Now, how to make it, we will discuss. Okay. How to increase the current rating, how to increase the voltage reading rating, all those things we are not going into. We are only talking about that the voltmeter should have a very high impedance to avoid any loading effect. Similarly, the ammeter effectively should have a very low impedance, almost zero, so that it does not change the current in the network. That is the two rules, right? That it should remember. Because if it has almost negligible impedance, then the current will not change in the network. Whatever it was previously, it will be same, like this 5 ampere example. If Rm is 0 for the ammeter which is connected in series to the network, it is almost, it is like it is not there in the network, right? It is not loading the network because it is not changing this current value because Rm is 0 almost. So the current is not changing, and that is what we exactly want. We don't want the current through that branch to change because of the plugging in of the instrument itself. Instrument should not load the network, right? So for an ammeter, the design of the effective internal impedance of the ammeter, whatever instrument you are designing, should be very low because it needs to be connected in series to the network in the branch. So it should not load the network, and hence its impedance should be very low. And for voltmeter, its impedance should be very high because it is generally connected in parallel to the network, and hence it should not load the network, for which the impedance should be very high. These two rules are clear, right? Okay. So what we are covering is now going into the instruments, right? Basically the numericals, and through the numericals we'll learn how we'll do that. So basically, before going to the numericals, now the thing you were talking, you must have learned about PMMC and MI type instruments, right? That some idea you should have regarding permanent magnet moving coil and moving iron type instruments. Basically, it is taking the help of magnetic fields. When you pass the current, you have energized the coil, and it always wants to align with the magnet, right? The low impedance, low reluctance path we say, right? Always magnetic field lines will follow the low reluctance path. And whenever the electromagnet is activated by passing the current, it works, it deflects. And there it's so that the deflection do not go to the extreme end, because for a very small amount of deflection, your pointer will deflect and not stop, right? So we built a mechanism with help of spring to control that, right? Whenever you keep passing on the current of 5 ampere, let's say, it will produce some torque continuously. Now that torque should be counterbalanced by something so that it goes to a steady state value, right? The pointer should go show a steady state reading. So we build the control torque, and we know the deflecting torque is due to the current that you are passing. So please remember, even if you are trying to use it as a voltmeter or you are trying to use it as an ammeter, for both the type of instruments, the excitation parameter is the current, right? Because for voltage also the meter should have some impedance for which there is some current, and it activates the deflection, right? Up to this it is clear, right? Because without current, how can we create the field, right? So we apply the meter to some voltage or some current which we want to measure, that leads to a current, that leads to the deflection, right? So the PMMC or the MI type instruments can be used as an ammeter or a voltmeter. Basic principle remains same, that it has to create some deflection. Accordingly, we'll create the scalings in the instrument, that it is okay, it is for 200 volts, it is for 400 volts, or if you want to use it as an ammeter, so you will also use the scalings in the meter. You will level it as per the quantities of currents that you inject, and based on the the spring constant and the design, the choice of the impedance and the design of the instrument, you label it that okay, this is for 1 ampere, this is for 2 ampere, and this is for 3 ampere, and like that. So a PMMC meter, which you can model like a resistance, right, of the coil, Rm. You can use it both for voltmeter and ammeter. But what I told you, that voltmeters are generally having larger impedance. Should have. Otherwise, they will load the network, right? Because this Rm value, the coil resistance value, is generally very small. And we cannot use it as a voltmeter until and unless its that is impedance is increased. So what we do? To use the same meter for voltmeter for voltage measurement, for high voltage measurement, or maybe for some value of voltage measurement, we increase its internal impedance by plugging in some larger value of resistance. and then you can connect it to some element to measure the voltage. Then it will not have loading effect, right? So accordingly you scale it based on the necessary voltage that you want to measure. This R external is also to be chosen in such a way that this current I does not cross IFSD. Do you know what is the meaning of IFSD? It is full scale deflection current. Generally, with RM being very small for the meter, the full scale deflection current is also very small. But we want to measure with that full scale deflection current a larger voltage. So what we do? We fictitiously want to make the meter see a small current for a larger voltage. What is the way to do so? By plugging in some extra resistance, so that you increase the effective impedance of the network or the meter, and effectively it will also produce a small meter current for a larger voltage. That is the technique we do. To use a PMMC instrument with a small impedance, with an inherently small internal impedance as a voltmeter by increasing the internal impedance by connecting some R external. So to use it as a voltmeter. And they give you some forms of numericals also, that okay, let's say I full scale deflection is 10 milliampere and the coil is having 1 ohm resistance. Now I want to measure 400 volts with this. So what is the extra resistance that is required to make it use as a voltmeter? So can you do this small numerical for me? You know, I full scale deflection is 10 milliampere. So I also have the information that for 400 volts I need 10 milliampere current. And let's say it is a PMMC type, so it is a linear, right? It is a linear instrument. So what is the extra resistance? This is 1 ohm. So 400 by R M plus R external should be 110 milliampere. No, voltmeter not act as ammeter. Voltmeter is voltmeter, ammeter is ammeter. I am telling you how to realize a PMMC type meter as a voltmeter. And also how to realize a meter which is a PMMC with a small internal impedance as an ammeter. To actually read more values of current and more values of voltage. What is the technique that is used? To use a small resistance meter to sense or to actually use it in measurement of higher amounts of voltages and currents. That is the game of plugging in external resistances. For voltmeter, you plug in series external resistance of higher value, and for ammeter, to increase the current rating, you actually plug in smaller shunt resistance to increase the current rating, so that the full scale deflection current still remains the same even for a larger amount of current or voltage. That is the whole point. So for a voltage, you see this is the RM, which is 1 ohm, but now the voltage has increased. Okay, so R external should be what? You plug it in the equation, 400 by 10 milli should be equal to 1 plus R external. So R external should be approximately equal to, I can say, 40k minus 1 around. Okay, so around 40k, right? Similarly, if I want to use it as an ammeter, 1 ohm, and the full scale deflection current was 10 milliampere, but I want to use it as an instrument to pass more currents, let's say 5 ampere. I want to use this meter only to read 5 up to 5 ampere of current. Can it read like this? If I, what will happen if I just connect this meter to a 5 ampere? Its capability is 10 milliampere. So what will happen if I pull or if I push 5 ampere? No. What will happen if I connect this instrument without any external arrangement in series to a circuit to read 5 ampere? What will just happen? Just can you tell me? Yes, meter will burn. And if also meter does not burn, what will happen? That for 4 ampere also it will show full scale deflection. For 10 milliampere also it will show full scale deflection. For 5 ampere also it will show full scale deflection. Because its threshold has already passed, right? And we have already scaled it. So it cannot take the current, right? And if it also takes the current, the full scale deflection value is already reached. And practically what will happen? Since the meter coils are designed to take only 10 milliampere and we are pushing 5 ampere, then what will happen? The meter will burn or the coil will burn, right? So what to do? I want to still use it as a ammeter. As an ammeter, how to use it? It can only take 10 milliampere. Effectively, you lower the resistance. How to do that? The effective resistance of this meter should be lowered. Why lowered? So that if it is lowered, then it can take more current for the same amount of voltage. The current should be same through the meter and another parallel path should be added, right? So what we do actually, you told right, we actually do some shunt arrangement, right? R shunt, lower than R meter. So that when the 5 ampere comes, what will happen? 10 milliampere will go this way and remaining current will go through the shunt resistance. And they will again merge and combine here, right? This current and this current will combine to form this current and then it will pass through the network. So effectively the meter can be scaled up effectively. Meter does not know it is 5 ampere. Meter still sees 10 milliampere only. So effectively we can scale the meter to read 5 ampere. That is how it is done, right? So you know how to use it as a ammeter or voltmeter. And this technique is scale enhancement. Scale enhancement or multiplier setting using R external, right? So let's solve a numerical on that. So you know that the PMM, there are two types of instruments, the PMMC and MI type, and PMMC measures the average value and it is a linear, right? But it is not a, it measures the average value and it is sensitive to the polarity, right? But the MI type instrument is not sensitive to the polarity because it shows the RMS value and it can be used to measure both AC and DC. And it shows the RMS value, right? And accuracy wise, the PMC is obviously higher and the MI type is lower, right? Sensitivity wise also it is very sensitive and the MI type instrument is less sensitive because of the reason, and the power consumption is also more for the MI type instrument, because of the more reluctance it has to traverse, right? So sensitive, but sensitivity wise it is also the PMMC which is leading, right? So it is high. So first let us solve more problems and then we'll see maybe more explanation to the nature of the instruments, right? So try this problem, okay? Take some minutes to try this problem. I want to hear the answer, okay? So try this problem. Solved, right? It was easy. If you have solved, kindly can you let me know the answer? Or at least unmute and speak up the method which you are trying to use to solve the problem, right? Any idea or any suggestion how to proceed with the problem? Just feel free to discuss, okay? Otherwise, you will not understand the steps. You will just mug up the steps. But remember, if you don't understand the concept, if the problem is little bit twisted, then you will be not able to solve that. So feel free to discuss. And what is the starting point? What information is given? Because I can solve it in one line, but it will be not of any help, right? So you should understand all the concepts, right? Yes. And in a way, how to actually decode more into it. Full scale deflection voltage, FSD voltage is 75 millivolt and meter resistance is 4 ohm, means that IFSD is 75 by 4 milliampere, whatever it comes. Agreed, right? So let me calculate how much it comes. So it is coming 18.75 milliampere. So if you pass 18.75 milliampere, it will show full scale deflection. This much is clear, right? So this is the meter which is having 4 ohm resistance, and this is the 18.75 milliampere. So I told you the meter has lower resistance. Now I want to use it as a ammeter, right? So what I told you, how to use this as an ammeter to measure 30 ampere. So very high current it wants to measure, right? So I need a R shunt, much lower shunt value, and I want to push 30 ampere so that this much current at full scale goes here and the remaining current passes through the shunt so that both can merge and then form again 30 ampere at full scale, right? So how to do it? How to calculate this R shunt? No, yes, parallel, but how to calculate R shunt? So let's say this is I, right? So this is IFSD, right? At full scale I am telling. And this is I minus IFSD. So what you can tell? I minus IFSD, which is the current flowing through the shunt, into R shunt, this is the voltage, should be same as IFSD times Rm. Speaking generally, right? Let's derive some general formulas or general forms. So can you tell me what is R shunt? IFSD Rm divided by I minus IFSD equal to Rm by I by IFSD minus 1. Agreed, right? So if I know the value of meter resistance and current I want to read and the full scale meter current, full scale deflection current for the meter, so I can easily calculate, right? So you calculate R shunt. Here you know Rm is 4 ohm, I is 30, I full scale deflection is 18.75 milliampere. Don't forget the units. Minus 1, right? So calculate how much is it coming? Fast, right? It is one line problem. Understood the concept, right? Concept should be understood, right? So 30,000 divided by 18.75 minus 1, which is 1599, and 4 divided by 1599 is coming around 2.5 milliohms, right? Yeah. So R shunt is 2.5 milliohms around, right? Any doubt in solving the problem? This is how we do range extension or scale extension for the meters which inherently don't have that capability of sensing that high current. Or maybe we could have designed the same dual of this problem for the voltmeter, which we have already solved. We took an example, right, in the earlier slide. So these are all range extension techniques, right? So that we can use the same meter to measure higher amount of current. Agreed, right? Now, anything in this world is not free. So what is the drawback of this method? We can go on playing with like this. We can go on playing like this, right? We can push 1000 ampere also. We can push 10,000 ampere also. So is it possible, or what is the drawback? What is the drawback? Okay, it actually helps in range extension for up to a certain point. But what is the drawback? Yes, what is the drawback? No, why voltage of parallel not same? Always it should be same as per law of electrical engineering. When two networks are connected in parallel, the voltage across both should be same. As per the law of electrical engineering, the potential across two connected nodes are same, always same. It does not change if you see it from one side or see it from other side. KVL always holds true, right? But I am telling you there is some drawback. What is the drawback? Think. There is some problem here. What is the problem? By doing so, when you are trying to divert the remaining amount of current through the shunt resistance, which is of a low value, what cost you have to pay? This kind of meter will lead to high power loss. I square R, right? Because a high amount of current is diverted through a small resistance, it will obviously lead to a power loss, which is undesirable. So actually what we do, no, more parallel will again lead to the same problem, right? So for measurement of high current, we don't actually use such type of arrangements. We can use, generally for DC, we don't actually go very high current. But for AC, we can go up to very high current, but not using this method. We can use induction principle, right? That will not lead to a higher amount of power loss. You must have seen the clamps, right? AC clamps for a current measurement. Those techniques we can use. Magnetic induction we can use to go for very high amount of current measurement, because for very high current this method fails, right? Because of power loss. So see the next numerical and try to solve it, right? So you know that torque is BINA, right? So A is already given. Always convert to SI. And what is N? 100. What is B? 1 Weber per meter square. All in SI, right? IFSD is asked. So the torque, we know that at steady state, control torque and deflection torque should be same. Even at FSD, right? So this should be same. So I have this number. This should be equal to BIN. Now calculate this I. 10 to the power minus 2. 2 times for millimeter to meter conversion, right? And N should be 100 and B should be 1. So what is it coming? I value. Let's say 10 to the power minus 3 milliampere. We want milliampere. So what we are getting is in milliampere, if we want to calculate, it is coming 0.15 and you have divided by 100 divided by 900 multiplied by 10 to the power 4, right? So around 0.0167 milliampere. Is the calculation correct? Kindly check. So let me check once again, right? Yes, I think it is okay, right? No, sorry, it will be 10 to the power minus 3. You are not paying attention. Millimeter to meter, right? So there will be a 10 to the power minus 3 factor 2 times. So multiply by 100, right? So it will be 1.67 milliampere. Clear, right? So now go to the next problem. This was easy, right? Try the next problem, right? Yes, try. Yes, did you try? What is the answer you got? I'm not getting any response from your side. This is a good question. Spring constant K times theta gives us torque, right? Torque is what? Either in Newton meter. Now I can give you this K considering theta to be degree, or give you this K considering this theta to be radian. Now what will tell me what I told you? The unit. See the unit. Newton meter and degree. So K is nothing but Newton meter by degree. So you need to actually consider theta to be degrees, right? If it was given in radian, then theta would have been in radian. But here it is degree, so directly plug in degree. So what is the spring constant? 1.75 into 10 to the power minus 6. There is a micro. Multiplied by 90 should be equal to some torque. Calculate what is it coming? So B is 0.9 and N is 200 and A you can take as 1.5 into 1.5. Now it is centimeter, so 10 to the power minus 4 square meter, right? So it should come as divided by 0.9 multiplied by 200 multiplied by 1.5 into 1.5. So what is it coming? Let's see. So it is coming 3.88 milliampere, right? You got it, right? So it was easy. So let's go to the next problem, right? So calculate the next problem. Yeah, correct. No, what you got? 11.11. Yeah, correct. So it was simple, right? So 1.5 into 10 to the power minus 6 into theta is 100 degree should be equal to B into I into N into A. Oh, okay, so try the next problem. I think it is visible on your screen. Yeah, is the problem visible? Yeah, is the problem visible? Okay. Why you had a doubt, right? Why TC equal to TD? Because if TC is not equal to TD, then your pointer will not reach a, like your Newton's law, right? You draw the free body diagram in your class 11 physics. What you did there was just balance the forces on this body. Because if this body is stationary, what is the rule for a body to be stationary? First, the net force acting on this body should be equal to 0. So if one force is acting upwards, one force is acting downwards, then only if they both of them are same, then only the net force on this body is 0. And if the velocity, initial velocity of this body would have been 0, then only it would have been stationary. Otherwise, if it would have was moving with initially a velocity of 5 meter per second and the net force on this body is 0, then this body would have moved in the same direction with 5 meter per second, because there would have not been any acceleration due to net force becoming 0. So Newton's law. So similarly, the pointer, after getting to that place with damping, if the net force acting in this body is 0, then with damping it will die out, the velocity will die out, angular velocity I am telling. But for it to be stationary at a particular point, so that you can see the reading, the deflection torque strength should be counterbalanced by a opposite torque. Otherwise, what will happen if that deflection torque is continuously acting on this body? Then what will happen? It will accelerate, and the velocity will keep on increasing. And it will, even for small values, it will go to full scale because it has that velocity, right? So the torque should have been balanced by someone so that the actual value should have been, and also damping is very necessary. Without damping, you cannot have a fixed value because the velocity would not have been 0, right? Damping is also essential. So damping is all, yeah, it is happening naturally, right? With the friction and with the air, right? It is happening naturally. There is damping in nature naturally, right? Otherwise, the additional damping arrangement can be there, right? But TC should be equal to TD for a steady state reading, right? And that is actually done by the spring. So if you elongate a spring, it has a direction, has a tension or a force, you can say, in the opposite direction. So that is what we take into play. That how much ever you pull it, it will just pull it in the opposite direction. That is how much ever deflection you want, the same amount of force will be acting in the opposite direction. That is the property of a spring. So spring actually is doing the job of producing the control torque to actually balance the deflection torque and give the steady state reading for the pointer, okay, of the meter. So now calculate this one, this another problem. I think you can see the problem, right? If you are able to see the screen, kindly let me know, right? Because I cannot see it here. You are able to see the screen, right? Just let me check whether the screen is visible. I think it is visible, right? Or something is there. I think problem is also visible. Okay, so try the problem. So do you know the sensitivity? So it is generally ohms per volt, right? So generally what it means is that if it is too much sensitive, then either the voltage is small or the meter resistance is high. So that implies that even for a smaller voltage, it will produce the same amount of deflection, right? If it is highly sensitive. So it can also be written as 1 by I full scale deflection. So it is a measure of the meter characteristics, right? Where you actually know the meter resistance and actually know the voltage for full scale deflection, and you assess the parameter named as sensitivity, where you actually try to actually quantify with respect to another situation where you have another meter to assess the deflection capability. Like, right, for the same amount of voltage, two different meters can produce different amount of deflections. Now with the smallest amount of change in voltage, if it produces deflections, we tell that the meter is sensitive. So that's why the voltage term comes in the denominator, right? Or in other words, the full scale current. full scale deflection current. If the full scale deflection current is small, then it is very sensitive, right? For smaller currents, it can produce the deflection and can show you. Or if the full scale deflection current is large, then for smaller currents, the deflection is not significant. That is a quantification of the sensitivity of the meter, right? Nothing else. So if they are already giving you the full scale deflection current, then you can directly calculate sensitivity, which is 1 by 50 into 10 to the power minus 6. And what will be the units? Units are important. Ohm by volt. So I can get S is 10 to the power 6 by 50 ohm bar volt. Or else you can do it in kilo ohm also. Take a 10 to the power 3 inside, and then 1000 is like this. So you get 200 kilo ohm per volt. If they mention you need to give in kilo ohm per volt, you can give in kilo ohm per volt. Else you can give in ohm per volt. So check the problem what it wants, right? No, I think 20 will be there, right? Not 200. 5 by 100, right? Yes, 20 will be there, right? So this is the problem, right? So check the next problem. What will happen? It is an easy one, that if the PMMC instrument, if the control torque is too high, then what will happen? Too high means even if the deflection torque is a little not significant that much, and if it is little bit higher also, that is if the TD1 and TD2, TD1 let's say is slightly low and it is slightly more than that. For both cases, the control torque is significant. So the accuracy will reduce, right? Accuracy reduces because not significant deflection, right? So accuracy of the instrument will reduce if the control torque is too high, or in other words, the sensitivity of the instrument will be compromised. So option C is the correct answer. So tell this one, this is easy, right? A moving iron measures the RMS value. So it is showing you the RMS value 10 ampere. So peak current is 10 root 2. 14.14. But is it true? Peak current of the oscillation is being asked, right? So what is that? Can you tell me what is that? What is peak current of oscillation? This is peak of current, right? Measured. But is peak of current of the oscillation, right? What will be that? No. Think. No, why? Why 2 times? Can you explain? No. Not peak to peak. Where is the peak to peak? In the RMS, RMS is like this, right? If it is a sinusoidal signal and it is telling you the RMS value of this sinusoidal signal is V peak by root 2 is RMS, right? So V peak is RMS times root 2. Okay. So then what will be it be? So think about it, right? Why is it true or not? Because moving iron will give you RMS value. RMS value of this signal is already known, which is 10. The peak value is 10 root 2, right? I don't see any problem, but just think if it is true or not. Okay, so let's go to the next problem. Okay, so try this problem. So you know, deflection torque in this case is half I square dl d theta, right? The moving iron type, right? And the inductance variation with respect to theta is given. So at any point theta you can calculate, right? So if I already give you as a function of theta, then you can differentiate it. And the deflection torque is already given. So Tc equal to Td equal to 12 into 10 to the power minus 6, right? And multiplied by, so Tc is known, right? Multiplied by theta. Theta is not known. So 12 into 10 to the power minus 6 theta should be equal to half I square into dl d theta. So what is dl d theta? 5 minus 2 theta. Now I is known, right? 5. So 12 into 10 to the power minus 6 theta is 25 by 2 into 5 minus 2 theta. or 24 into 10 to the power minus 6 theta is 125 minus 50 theta. Or theta you can calculate, right? And since it is radian, please note spring constant was in radian. So what will the theta be? Theta will be also in radian. So theta, what is it? 50 plus. So theta will be 125 divided by 50 plus 24 into 10 to the power minus 6 radians, right? So what you are getting? Let us calculate. 125 divided by 50 plus 24 into 10 to the power minus 6. I am getting 2.5, right? Is there some problem? Yeah, you got 96.8, right? So what did we miss? Is it calculation is okay or not? Any calculation error? I think I did. So this is coming as 20. I think this is okay. Yes, and this is theta, right? Okay. So 24 into 10 to the power minus 6 theta, and this is 125 minus 50 theta. Then 50 plus 24 into 10 to the power minus 6 theta should be equal to 125. So what is the problem? 125 divided by 50 plus 24 into 10 to the power minus 6. Oh, there was a micro here, right? Okay. So there is a 10 to the power minus 6 term here also. This side, right? So I can cancel from both sides the 10 to the power minus 6 term, right? Everything else remains the same. So what it becomes? So there is 24 theta here, and then we can actually plug it in, and then we get theta as 125 by 50 plus 24. So 125 by 74 radians, right? So this is radian, and if you convert to degree, you will get 96.78 degree. So I think option 2 is correct, which you already have got, right? Yes, it is 1.689 radians, right? And if you convert it to degree, you get 96.78 degrees. So this is the correct option. So the micro was important, right? That micro we missed out. So that micro should be taken into consideration. So please take care of the units very cautiously. Like example, there is radian, right? So you need the angle will come in radian. That is also an important point. And there was micro here. So that was also important. So take the units very seriously in the exam, right? Yes, so this one just try. So this is a linear and this is a non-linear, right? As you understand, because it is proportional to I square, is proportional to I, right? So scale is non-linear. So at higher sides, first you will see like this. So 0, 1, and then it will keep on getting compressed, right? Smaller and smaller, because with higher numbers, the square increases more rapidly. So the scaling becomes compressed. So this is a non-linear scale. And this is a linear scale, right? Equispaced distances. So scaling is linear as theta proportional to I for PMMC. So to see the difference, check scale of two instruments, right? Just by seeing the scale, you can understand which one is moving coil or PMMC or which one is moving iron, because moving iron scale will be non-linear and will be compressed at the higher side, right? Understood, right? So because what is 2 square? 2 square and 3 square, because theta is proportional to I square, right? So 2 square, it is proportional to 2 square. So it is proportional to 4 and is proportional to 9. What is the gap between 4 and 9? Right? And what is the gap between 0 and 1? Yes. So for 1, I can actually allocate more numbers, right? Because what will happen for higher currents? It will actually lead to higher angles. But when you reduce the current, that angle will be further reduced, right? Because your control torque is what? Spring constant times theta, but your deflection torque is proportional to I square. So theta is increasing from 0 to, let's say for example 90 degree linearly. But 0 to 1 degree and 1 degree to 2 degree, it can incorporate, and 2 degree to 3 degree, it incorporates more higher values of current, because theta is proportional to I square. So let's say theta is equal to I square. Then you see, if theta is 0, I is 0. If theta is 0, I is 1. Theta is 1, I is 1. But if theta is 2, I is 1.4. And if theta is 3, it is 1.7. So initially the gap was 0.4. Now the gap is 0.3. So isn't it getting compressed? That's what I am telling. As you scale your theta linearly as 1 degree, 2 degree, 3 degree, 4 degree, between 0 and 1 degree, how much ever current you had, between 3 degree to 4 degree, you have more currents. So as currents increase, scales get compressed. Because for that same theta at the higher side, or same theta block, divided block of 1 degree at the higher side, you have to incorporate more currents, right? It has more currents. Understood, right? Whatever I am trying to tell you. So the scale gets compressed at the higher side. Because theta is I square, right? So what is I? I is root theta. So if theta is 2, I is 1.4. Similarly, if theta is 3, I is 1.7. Now you see, initially for that 1 degree, you have 1 to 1.4 current, which is a little more. But for 2 to 3, you had little less current, right? You may take also one more example just to see. 3 to 4, if you can take, it will be 2. Accordingly, you can just 1.78 you can take. 0.2 is the difference. So initially for 1 degree increment, you got 1 ampere increment. But again for 1 degree increment, you got only 0.4 ampere increment, right? So initially the ampere scale would have been large, right? Much more spanning of lower values. But now the ampere scale is have to be reduced because there are more values of currents coming in. So 0 to 1 degree I can say is 0 to 1 ampere. But 1 degree to 2 degree now you have 1 to 1.4. Like this. So what you can do? You can prepare a non-linear scale, right? Because theta is linear but the currents are non-linear, right? Clear or not? So let's see the problems on wattmeter. As you know, wattmeter I can say so it's actually having a pressure coil and a current coil. Pressure coil measures the voltage. So you have the common connection here. And you actually connect this across the load. So sorry, I wrote the opposite actually. So this is the current coil and this is the pressure coil because it actually measures the voltage across the load. And this measures the current going into the load, right? Current coil. And accordingly, your power will be V into I, right? Obviously, and the angle between them. So cos theta, right? Now, actually, there is a n-1 wattmeter method where you know that for three-phase AC circuits, if it is n, you need n-1 wattmeters if the system is balanced, right? So for three-phase balanced system, only 2 wattmeter is sufficient. So actually what we do, if we have R, if we have Y, we have B, we connect one wattmeter like this and another wattmeter like this. So this is called as W1 and this is called as W2, and this is the load, right? So consider a balanced system like this, and this is the sequence like R, then comes Y, then comes B, right? So RYB sequence. Then your wattmeter 1 will read what? This is the line voltage VRB times IR times what is the angle between the line voltage and the phase current? 30 degree. Plus 5 and 30 degree minus 5. Why? Because you know that maybe VR, this is VR, this is VY, this is VB, and this is the current, right? IR, IY lagging, and IB lagging by theta, all balanced. Then what will happen? VRY will be like this. VY minus will be there, and then VRY. This is 30 degree, right? Because this is 120 degree and this is 60 degree and bisecting, so 30 degree. So 30 plus 5 will be there, cos of angle between them I told you. So theta or phi plus 30 degree, and another wattmeter similarly will read VYB into IY into cos of 30 minus theta. 30 minus theta or theta minus 30, all are same. But these are all balanced, right? So I can write as line voltage and line current. All are same, magnitude wise. So what is the value coming? W1 plus W2. Can you check? And also check W2 minus W1. Right. Find these two values, what they are coming. So when you do this, you will find that this will give you root 3 VLIL cos phi. And this will give you VLIL sin phi, which is nothing but the three-phase reactive power. However, the root 3 is missing. So by root 3. And this is giving you the three-phase active power directly. So if you want to find the Q3 phase, it will nothing be but root 3 W2 minus W1, and active power will be W1 plus W2 in this configuration. So if we know Q by P is the, as per the power triangle, sorry, this is Q, right, and this is P. Just to find the power factor, right? Okay. So what is theta? Tan inverse root 3 W2 minus W1 by W1 plus W2. So what when W1 equal to W2? Just a case study. Power factor is theta is 0. So cos theta is 1. So UPF, right? Yes, like that you actually determine by the 2 wattmeter reading. So this is the 2 wattmeter method, right? So just we wrote the answer for you. You try this. That W1 and W2. W1 is 2000 or 2 kilowatt and W2 is 1 kilowatt. Then they are asking the reactive power Q3 phase. Now we wrote the formula that Q3 phase is nothing but W2 minus W1 by multiplied by root 3, right here. So that will be root 3 times 1000. That will be 1780 around. But the unit will be like this, right? Or 1000 root 3 kVAR, right? Understood, right? These are basic, right? So I'm not just explaining more. I think you can understand from the slide. So power factor is 0.5 they are giving, then 1 wattmeter will read. So power factor is cos theta is 0.5. When will it happen? So tan theta is root 3 W2 minus W1 by W1 plus W2. And what is the cos theta being half, meaning theta is 60 degree. So put theta as 60 degree, it will get tan 60 is root 3 equal to root 3 times W2 minus W1 by W1 plus W2. Then what will happen? W1 plus W2 equal to W2 minus W1. Then one of the wattmeter reading is coming 0. So 0, right? These are all easy, right? Just plug in into the equation and check. Okay, so now come to the energy meter problem. So they are asking the load, right? And you know that meter constant K is defined as number of revolutions per unit energy, right? And 1 unit of energy is nothing but 1 kilowatt hour. That is how they call it. So if there is the meter constant given as 1200, that means 1 unit of energy, to record 1 unit of energy, there are 1200 revolutions by this meter. This is the meaning of meter constant. So if it makes 20 revolutions, so if the meter revolves 1200 times, in 1 hour, will record 1 kilowatt of energy, 1 kilowatt of power for 1 hour, then it will have to revolve 1200 times. That is what is the meaning, right? So now it is giving you that it is revolving only 20 revolutions and 30 seconds. Then what is the load? In kilowatt they are asking. So energy is nothing but kilowatt into time in hours. This is the energy, right? Then how to do it? So what is the emitter constant? 1200 by 1 kilowatt hour. So for 20 revolutions, what will it be? One point to know. Twenty revolution, it will be what? 1200 revolution, 1 kilowatt hour. 20 revolution, 1 kilowatt hour by 1200 into 20. This will be the recorded energy. This is the recorded energy, right? You plug it in here and you will get it. So what is the recorded energy is 1 kilowatt hour into 20 by 1200. Now you are being asked the kilowatt and time in hours. So 30 seconds only it revolves. So 30 by 3600 hours. You do it and you will get it, okay? So you'll get the kilowatt, right? How much kilowatt? So hour is getting cancelled, right? How much kilowatt I can tell. So it is coming, I can say kilowatt is nothing but 3600 into 20 by 30 into 1200, right? So 2 is coming, right? So 2 kilowatt. Understood, right? So simply from the meter constant or energy meter constant, you know that 1 kilowatt hour it will record if it is allowed to revolve 1200 revolutions. But I told you only 20 revolutions. So 1 by 1200 into 20 kilowatt hour will be the reading. Now I know also that energy is kilowatt hour, kilowatt into time in hour. So accordingly you can plug it in and then balance to get the equation and find the wattage, right? Load in kilowatt. No problem, right? I don't think it has any problem. Just see it once again, you will understand the problem. Again, here is another problem of another variant. Just try it. So actually meter is having some error inside it. So it is taking 86 seconds and 50 revolutions. And the load is 4.4 kilowatt, right? So what is the measured energy? Because 86 seconds it is taking and the load is 4.4 kilowatt. So what is the recorded energy? 4.4 into 86 by 3600 kilowatt hour. This is that the energy meter is telling you. Now you have to check if this is true or not. From the meter energy meter constant, first let us see how much it is telling us. 0.1051 kilowatt hour. This much units is what the energy meter is telling us. But what should be actual? You know that 500 revolution for 1 kilowatt hour it should do. Now how many revolution it is doing? 50. 0.1 kilowatt hour it should be. But it is showing me 0.1051. So there is an error of 1051 minus 0.1 with respect to 1 into 100%. This is the percentage error. And how much is it coming? Yes, calculate. So sometimes you can do with respect to actual, then it will come as 5.1%. Or you can do like this, that actual minus measured by measured. It will be told that how to find the error with respect to what. Then you can get minus 0.051 divided by 0.1051 into 100. Minus 4.85%. Both ways you can do. Both are correct, right? Yes. So both are correct. Now let us come to the final topic, which is the Lissajous plots. And I just want to briefly discuss with you how to actually find out in the Lissajous plots the phase shift and the frequency information. So what is it? In the scope, you actually have in the x-axis the sweep or the time signal in the ramp form, and the plot. like this. So this is the time axis mode, or you can tell. And in the XY mode, what you do, you actually have two signals, Y and X. And it leads to some formation of plot. So X is a known signal, and from the nature of the plot, which is also known as Lissajous plot, in the XY mode of the DSO or the oscilloscope, you can tell, you can determine the phase shift and frequency. Obviously, they are assumed to be some forms of sinusoidal signal, then their analysis and shapes are easily understandable and easily we can find out, right? So let's say Y and X are two signal and X is A sine omega t, we give it. And then in the XY plot, if we find a circle, then what it implies? 90-degree phase shift and same frequency. Then what will happen? A cos omega. Because 90-degree phase shift, right? But no change in amplitude and frequency. But for ellipse, omega same. That is, we can tell omega x, omega y, and omega x same. But 90-degree phase shift and unequal amplitude. And straight line if zero phase shift. Obviously, amplitudes can vary, but omega same. So amplitude will vary, then slope will vary. But how to mathematically find out? How to find frequency and phase shift of unknown signal? So if you have some kind of plot and you know the intersection point height and the extremum height, then if I call it y1 and y2, or if you know maybe this length x1 and x2, the intersection length and the extremum length, then this phase shift of y with respect to x can be achieved as sine inverse of y1, y2 by y1, or same as sine inverse of x2 by x1. And the frequency of the unknown signal with respect to the known signal can be determined as number of horizontal intersections by number of vertical intersections. Just we'll see how. So these two are very important formulas. And from the nature of the plots, you can also identify the remaining information. So solve this problem. See how many intersections with respect to the intersects? So vertical we have 4, horizontal we have 2, 1 here, and here it is 4, right? 1, 2, 3 and 4. So omega unknown by omega known, or in this case they call it omega 2 by omega 1, should be horizontal by vertical or half. So omega 2 is omega 1 by 2. And another information they ask about the phase shift. Phase shift is nothing but sine inverse see here the extremum height and the intersection height both are same, right? So you can plug in y by y you can tell, or x by x you can tell, where this length is x and this length is y. So it is nothing but 90 degree, right? There is a 90-degree phase shift, and they are already given 2 signals are sinusoid, right? So you know only the phase shift is required. So phase shift is 90 degree, means that this will be theta, right? So sine theta becomes cos theta, or sine omega 1t becomes cos omega 2t, right? So this one is the correct answer, option B, right? Any doubt? Any doubt, you can just let me know, okay? Because 2 sinusoidal signals they have already specified. So accordingly it will be a cos omega 2t and then half of the frequency, right? So coming to the next one, as you can see, this is a Lissajous pattern given with respect to xy plots, right? And it is given that the frequency of the x is known as 250 hertz, right? And then they are asking you the frequency of y, which is the unknown signal. So just calculate how many horizontal and vertical intersections. So how many horizontal intersections? First tell me. 1, see, 2 and 3, 4 and 5, 6 and 7, 8. So 8 horizontal intersection, and 1, 2, then 3, 4 and 5, 6. So it will be 4 by 3. So if I know fx, then fy will be 4 by 3 into 250. Around 333 hertz it will come. And similarly for the next problem, I can tell that there are how many horizontal intersection? 1 and 2. But vertical intersections are 1, 2, 3, 4, 5 and 6. So 1/3. So if I know fx, which is 400, then it will be 400 by 3, or 133.33 hertz. Accordingly, you can find out the frequency information. These are simple, right? Similarly, for this one, you see 1, 2, 3. 3 are vertical, and 1, 2, 3, 4. 4 are horizontal. So unknown by known is horizontal by vertical, right? Then again, if it is 450, then I know it will be coming around 600 hertz, right? Because it is 150. So accordingly, you can solve for the least adjust plots, right? So with this, we can end the session, and I think you will be able to solve most of the problems with this information, right? So if no more doubts, I think we can close the session, right? And you can also post your doubts in the email or in the group also, right? So any more doubts, or else we can already close the session because we are already reaching the time. So I think you have learned the concepts and you can solve the assignment problems and also the problems coming in the exams. Just see the videos once again, the live sessions that we have conducted, and the sheets also are uploaded. So with this, I can tell that you can, if you solve properly and practice properly, you can do good in the exam. So best of luck for your exam, and with this, I want to close the session, right? So thank you, and we can leave the session, right?